So remember that the polarization of an electromagnetic wave describes the orientation of the electric field relative to the propagation axis. Right? In this picture, I've shown the electric field oscillating vertically, and of course then the magnetic field is horizontal. But for the most part, we're going to ignore the magnetic field, and we're just going to focus on the electric field. So this would be a case of the electric field oscillating vertically. Right? We call that a vertical polarization. But you can have other orientations of your molecule, and you can have a case where the molecule is oriented horizontally, in which case you would have, or oriented in such a way that the electrons move horizontally when excited. In that case, the electric field would oscillate in the horizontal direction, and we call that horizontally polarized light. Right? Of course, you can have every possible orientation in between, and when we look at something like sunlight or just like a lamp, we generally have every possible orientation of molecules, and so we have every possible orientation of electric field. We call that unpolarized light, but really unpolarized light is really what we should really call randomly polarized light. The light has polarization, it's a mixture of every possible angle of polarization. Now what we can do is we can take unpolarized light, which is really a mixture of randomly polarized light, and we can pass it through a filter called a linear polarizing filter, right, and turn it into polarized light. So these polarizing filters are made up of long molecules that like to absorb in one direction but not much in the other. And so in one direction, the light will be heavily absorbed, but if the electric field is oscillating in the perpendicular direction, the transmission axis, then it will pass through the filter unabsorbed. Right? So if we orient the transmission axis to be vertical, then after the polarizer, we'll have vertically polarized light. And we'll come back to this transition between unpolarized and polarized light in a minute. Let's just use the first polarizer and use that to create linearly polarized light. But let's just say we start off now after this first polarizer, and we'll just look here. We have polarized light. We have some certain amount of intensity of this polarized light right here. And what we're going to do is we're going to pass it through a second polarizer. But when we use a second one to look at light that's already polarized with a second filter, we call that filter an analyzer. It's just a name. Okay, so we take a second polarizer, which we call our analyzer, and we're going to now rotate this polarizer so that its transmission axis is at an angle to the polarization of the light that we have right here. We can find out how much light will make it through using what's called Malice's law. That says if you take the amount of light before the filter, right, this is the amount of light before the filter. We're looking at the analyzer here, filter 2, and we look at the relative angle. Right, so this really should be like a delta theta, but they call it theta, so we'll leave it that. We'll keep that notation. We want the relative angle between the polarized light and the transmission axis of the analyzer, and we take the cosine of that squared and multiply it by the initial intensity, and that's how much intensity comes out. So the Malice's law tells us how much the intensity is reduced by going through this second polarizer at this angle theta relative to the polarization of the initial light, of the incident light, I should say, on that filter. And what comes out is going to be possibly less intense, and now that light will now be oscillating in the direction of the transmission axis of the second filter. This is a pretty simple equation to plug into, right? If you have a certain number of watts per centimeter squared here, a certain amount of intensity, then if you have this at 0 degrees relative, right, meaning there's 0 degrees difference between the axis of polarization here, right, and the axis of this filter, right? So if we made the analyzer vertical as well, cosine of 0 is 1, 1 squared is 1, so you get all the light back, right? It just goes straight through. If I rotate this to 90 degrees, right, so that now this is horizontal, but the incident light was vertical, then the theta difference between these two angles is 90 degrees. Cosine of 90 is 0, squared is still 0, times anything is 0, so the amount of light that comes out is ideally nothing, right? Totally blocks all the light. Any angle in between, you're going to have some number between 100% and 0%, right? So let's look at that. Let's look at a case where, well, if you plug in 45 degrees, cosine of 45 degrees is 0.707, and that squared is 0.5. right? So at 45 degrees, you'll get the light coming out is half as intense as the light that was coming in, and it will be at now the 45-degree angle of the analyzer. But let's look at a more general case. Let's look at what happens when unpolarized light comes through and the first polarizer, right? What happens between here and here? How intense is this light compared to the initial unpolarized light? And the answer is it's half as intense. And let's see why that is. To see that, maybe the easiest thing is to go to a spreadsheet here. So I made a little spreadsheet where I'm just taking Malice's law and plotting it for every possible angle between 0 and 90, right? And just to keep the short list short, we're just doing five degree steps. And we'll take Malice's law of each one of these. So like we already said, at 0 degrees, it works out to be 100% transmission. At 90 degrees, it works out to be 0% transmission. If I rotate the polarizer to be just 5 degrees off of the polarization of the light, it turns out that 99.2% still gets through, right? Because what I can do is I can decompose the light that's at 5 degrees relative to the transmission axis into a component that's parallel to the transmission axis and a component that is perpendicular to it. And the component that's parallel gets through. The component that is perpendicular, which turns out to be just 0.8%, gets blocked. But you notice in this list a symmetry, right? For this angle, 0 degrees, there's a 1, and at 90 degrees it's 0. At 5 degrees, it's 99.2, but at 85 degrees, it's 0.8% transmission. At 10, it's 97%. At 90 minus 10, or 80, it's 3%, right? So this plus this is equal to 1, so the average of those two is 1/2. This plus this is 1. The average of those two is 1/2. Average of these two is 1/2. Average of this plus this one, which is 90 minus 20, is 1. So the average of those two would be 1/2. And in the middle, you have a 1/2, which means that you take the average of all of these rays, the amount that passes through, averaged over all these rays and all these angles, is 1/2. So unpolarized light, each of these rays will let some component, with the exception of the ones at 90 degrees, will have some component that sneaks through. And when you average together all those components that sneak through, you end up with 50% of the light making it through that initial polarizer. And now the light has gone from having every possible polarization to only having the polarization along the axis of the first polarizer's transmission axis. Okay? And then from there, if it goes through another polarizer, then everything's at this one angle relative to the transmission axis, and you just simply apply Malice's law. All right. So, clicker question, which won't be a clicker question, but just something you should work through at home. If we take two polarizers and we line them so their transmission axes are parallel to each other. So let's to pick an angle, let's say the first one is vertical, and we make the second one vertical, right? This allows the maximum amount of light to be transmitted through the pair. The question is, how much do I have to rotate the second polarizer to go from that maximum transmission to a minimum transmission, which ideally would be 0. Taken two polarizers, and I've put a little piece of tape on to indicate the transmission axis of the polarizers. Okay. So when both tapes are at the top, that means that the two transmission axes are both vertical. And if I rotate one by 90 degrees, from here to here, you see that you go from totally bright to totally dark in 90 degrees. Yep, so the answer is 90 degrees, right? So you can easily get to this answer by using Malice's law, right? You see that I is equal to I max means that cosine squared of theta must equal to 1. So clearly theta max is 0, right? And that's what we said. The two are aligned. To get to the minimum, we want I equal to 0, which means we want cosine squared theta equal to 0. And cosine squared theta is 0 when cosine of theta is 0. Cosine of theta is 0 when theta is 90 degrees. That's the mathematical solution, but you can kind of logic it out, right? The light that exits the first polarizer is linearly polarized so that all the electric fields are parallel to the transmission axis, which is vertical in our case. To maximally absorb that linearly polarized light, which is now vertically polarized, the transmission axis of the second polarizer would need to be horizontal, right? Completely perpendicular to the light. So that means we have to rotate by 90 degrees. Let's now take three linear polarizers that are aligned so that the first polarizer has its transmission in the vertical axis, right, vertical direction. The second polarizer is at 45 degrees, and the third polarizer is completely horizontal. I'm going to make the claim that when I have it like this is going to allow the maximum amount of light to be transmitted through the triplet. They should say triplet. How much are you going to have to rotate the second polarizer to reach a minimum transmission, which for ideal polarizers would be zero transmission? So we'll add a third polarizer. This one has blue tape showing where the axis is. We're going to now align them to the configuration we said we would start with, which is to have the second one at 45 degrees. Okay, so when we have it 45 degrees here, it's at the most transmission we can get through, and I only have to rotate it by 45 degrees to get it to reach a minimum transmission, or pretty much black. All right, so let's go back to the slides. The answer is 45 degrees. And formulaically, using Malice's law, here's how we see that. Now, conceptually, what's happening is I have initially this one vertical, second one at 45 degrees, and the third one vertical, horizontal. Right? So the light coming off through the first one is now vertically polarized. That vertical polarization, since this axis is at 45 degrees, if I kind of view the axis as one here and one here, right, these two perpendicular axes, then something that's got this direction can be thought of as having a component along the transmission axis and a component along the absorption axis. And at 45 degrees, it's half and half. So half of the light gets absorbed and half of it gets transmitted. And of that half that gets transmitted will have to be along the direction of this polarization of the polarizer, which means it's now, the electric field is now oscillating at 45 degrees like this. Then it hits this third polarizer, right? And the third polarizer has this transmission axis this way. And the light is now at 45 degrees, but we can break that down into a horizontal or transmission component and a vertical, which for this polarizer would be the absorption component. So again, half of that light gets absorbed and half of it gets transmitted through, and then the light that finally comes out is polarized horizontally, right? And that's giving us a quarter of the light coming through compared to what was past the first polarizer. Only a quarter made it through because only a half made it through the second polarizer, and then only half of that made it through the third polarizer. When we rotate this thing by 45 degrees, so that the second one is now horizontal, then what's happening is this is vertical and that's horizontal, and nothing gets through, which means there's nothing coming into the third polarizer, so it doesn't matter, right? The other option would have been to rotate it by minus 45 degrees, in which case this is horizontal. I'm sorry, this transmission axis is vertical, this transmission axis is vertical, so all of that light that made it through here makes it through the second one. But then when it gets to the third one, this one's perfect. The light is now perfectly vertical polarization. It hits something that's perfectly horizontal transmission axis, and none of it gets through. So either way, when this middle guy is aligned with this guy, or if it's aligned with this guy, it will end up blocking all the light through this triplet, right? And you can imagine if you kept going, once this reached, if I turned this green middle one down to this angle, you would again be back to transmission. And if we moved it down to here, then basically it's vertical again, so they would be blocked again. All right.